my talk, I want to assure you that I am not anti-Mars. And to prove that to you, I have worn my Mars, my one and only Mars shirt that I bought from Buzz Aldrin's online store. And I think many of you will appreciate it. It says, "Get your butt to Mars." Of course, he has another one with this little stronger epithet, replacing butt with something else. But since I have young children, I didn't get that T-shirt. So, anyway, I should always thank my funders, and that is this Nexus Collaboration that Tony Del Genio, as you all know, is the PI on our group here. We're the Rocky 3D group in the Nexus Collaboration that's based on most of our galleries that does this stuff, and there's an exoplanet climate group that we're a part of at Goddard Space Flight Center. Those of you who have not heard of that. Sean Goldman and a few others lead that group, and of course we work at NASA. And these are some of the people that have helped in this work: Tony, Nancy, Linda. Tom Clooney helped quite a lot with fixing up the calendar in Model E so that we could study slowly rotating planets, and faster rotating planets for that matter. Igor's helped in all kinds of ways, and as you all know, Max helps with everything. Without Max, none of this would be possible. And of course, Jeff also helped us out with some topography stuff, which I'll show. So, I've been giving this talk to a diverse audience. 2 weeks ago, I gave it in Japan at a conference, and then last week I gave it at Goddard. Last week I had to show this picture because astronomers who I normally talk to and physicists don't know anything about Earth science nomenclature. But I think you all know what these epochs are: Hadean, Archean, Proterozoic. If you don't, memorize those numbers very quickly. Anyway, okay. So I want to talk about this idea that Venus might have been the first habitable world of our solar system. I'm going to make a lot of assumptions, as I said in my talk, but maybe not as many assumptions as people make to make Mars an early habitable world. But that's the idea behind this. So let's talk about what the habitability needs are. What do we mean by habitable, right? Always NASA says, the mantra is, find the water, look for the water. We want a kind of a planet that has liquid water on its surface, some kind of liquid water beneath the surface. I think one thing that's not mentioned very often in these discussions about habitability is stability of the climate. I think I don't have to convince any of you here about the importance of having a stable climate. And what I mean by stable climate, I mean over long periods of time. Life is probably not going to start up on Earth after a million years of everything just being right. It's probably going to take longer than that. And that requires things, again, that everybody here is familiar with: plate tectonics, exposed continents, weathering, volcanism, and of course on Earth, biology plays a big part, as you all know. Okay, let's talk about two other things that will impact this study of looking at Mars. First is the faint-young sun paradox. I assume you all know about the faint-young sun paradox. And habitability through time. I will only use these acronyms once more in the next slide, so you don't have to memorize them. So let's take a look at Earth and Mars versus Venus. So I think we all know from the faint-young sun that we've had a really hard time getting Earth warm enough in that early Archean period, given the faintness of the sun. We have to do funny things to our atmosphere to keep liquid water on the surface. It's even harder to get Mars warm enough for such a thing to be true. What always cracks me up is when I see pictures of Martian oceans from 4 billion years ago, is how they show it from space like the atmosphere would be that optically thin. It wouldn't be that optically thin. You wouldn't be able to see any ocean, if it even had one, from space, because the atmosphere would be so optically thin to capture every single photon of energy to keep that atmosphere warm. You probably wouldn't see anything. We also know, at least I think we have pretty good constraints, that there's been no Martian magnetic field or plate tectonics on that planet. I mean, by plate tectonics, global plate tectonics, for at least the last 4 billion years. And here's some references to back up my statement there. And here's a picture that I pulled from this guy Harmon, 2013, showing where early Mars actually sits, and he actually puts it outside the habitable zone. That's never mentioned in these discussions about early Mars being a really good place for life, even in studies looking at habitable zones around our star and for worlds, they even put Mars often outside the habitable zone. And it says early Mars, note, not modern Mars. Okay. So how about for Venus, my faint young sun, and my habitability through time? So I want to talk about some things that may be able to help me. So the first thing is, with a faint young sun, I get a lower solar flux in the time period I'm interested in. So I'm talking about 3 to 4 gigayears ago, about 20% less luminous than it is today. We do have some evidence for water. The D to H ratio does tell us something about that. I'm going to show you why I believe that Venus could have had a slowly rotating, what could have been a slowly rotating planet back 3 to 4 billion years ago. Whether it had an N2 rich atmosphere or not, like Earth, is not known, but I'm going to show you some constraints on that, and the question about plate tectonics, of course, to give us that climate stability. So these are just some plots of our sun's solar flux through time. This is written by an astronomer. So astronomers like to start beginning not from today, but from the beginning of whatever it is they're talking about, whether it's the universe or in this case the sun. So you can see brighter is closer to today, and then as you go back in time, it gets fainter. So that's what the solar spectrum will look like. Of course, I'm not showing you all the UVN, which of course will change when the sun is really young. I'm not going to talk about that period when the sun is super young. Okay, let's talk about water abundance. I think most people believe that Earth and Venus received around the same amount of water at the beginning of the formation of the solar system. We see a high D to H ratio on Venus today as compared to Earth. It's about 150. And from that, estimates have ranged that the planet could have had between 4 and 530 meters of liquid water spread across the surface. The problem with using, sorry?
How is that the same amount as we have?
How is that the same amount? I said roughly the same amount. I said in the beginning it probably received about the same amount, and the D to H ratio puts constraints on how much they think there actually
we
was.
Have what, like 1 or 2 kilometers, right?
Absolutely, absolutely.
So that's really a lot more, even the upper range.
Yeah, but we don't know what happened to its early water inventory. There's a lot of theories about whether Venus's early water inventory was lost for several reasons, which I won't have time to go into, but I'll be happy to discuss with you afterward. Or if it's deep down in the mantle.
And just in case that 530 number is clearly less than what we have received.
Yes, I said the D to H ratio today gives you constraints on these numbers. The problem with the D to H ratio is that we don't know when.
So then in that case, the first statement is not true because they didn't receive the same amount.
No, I said we believe they received the same amount in the beginning of the formation of the solar system. Planets can lose things. We believe that Venus probably lost some of its water in the beginning of its history for reasons that I don't have time to go into.
So what does the 530 meter mean? What's that number there?
I said this number comes from the present day measured value of the D to H ratio. This is how much the atmosphere tells us water is lost as of today. The problem is we don't know when it was lost over what period of time. We don't know if this water was lost over the last billion years, over the last 4 billion years.
So you think that maybe some other water was lost in other ways?
Absolutely.
Okay.
Absolutely. But, as I guess I was trying to say there, this kind of early dry or wet hypothesis is basically impossible with our present knowledge. And we really need more observations to tell us what the early inventory was. Basically, we need some in situ observations, which we don't have so far. We need some noble gas isotopes and other isotope measurements to get a better handle on what it might have been early on. Okay, how about Venus's slow rotation? So back in 1980, Dobrovolskis and Ingersoll have this well-known paper where they say that it's Venus's thick atmosphere and the tidal interaction of the atmosphere with the sun that gives Venus its retrograde rotation, in essence. I know many people think it's because there was a giant impactor, and whenever you see tables about the planets. Venus always has a negative number for its rotation, but all you need is a thick atmosphere. At least that was believed for a long time. But just this last year, LeConte and collaborators wrote a really nice paper using another model where they showed that you don't even need a thick atmosphere to get Venus to have its present day rotation rate. A thin atmosphere will do the same. There's enough tidal interaction with a thin atmosphere. So my point here is that I don't need to have a thick atmosphere to get Venus to have the rotation rate that it has today, and I want that rotation rate today for my ancient Venus for reasons which I'm going to show you in a little while. Okay. These are the carbon-nitrogen budgets for present-day Venus from a paper back in 2000. I think many of you might be surprised to learn that Venus has a lot more nitrogen in its atmosphere than we do. You don't think about it when it has 90 bars of CO2, but it has a couple bars of nitrogen also in its atmosphere. Now, the question is, can we put constraints on how much nitrogen the atmosphere would have had in its early history, assuming that there was a carbon cycle and carbon wasn't completely gassed the entire atmosphere on Venus as it is today? And I've been trying to read papers on what kind of nitrogen sinks there would have been and are present day on Venus. And so far, the only ones that I've come across are solar wind stripping, basically. Closest, and I did a back of the envelope calculation just today, and lightning offers you almost no respite, basically. So, not sure what the primordial abundances of nitrogen were in the atmosphere, but there's a lot of nitrogen around if I want to use it for something. So as I kind of said before, cosmochemical and geochemical models imply that the bulk composition of our sister world, and I've actually called her stepsister worlds, it's quite a neglected world, as it were, are very similar. One problem with studying Venus's geology is that the planet, not completely, but for the most part, has been resurfaced in the last 750 million years to a gigayear, which makes it difficult. It's also difficult to study the surface because the atmosphere is so thick that only very large meteors make it through that atmosphere without being broken up, so we only have fairly large craters. There's almost no magnetic field on Venus today. We like our magnetic field on Earth for reasons that everyone in this room is very familiar with, but we don't know if it had a primordial magnetic field. I don't think we really understand, from the papers I've read anyway, when Earth's magnetic field really took off and why Venus's magnetic field is not running today. I mean, there's arguments about spin and other things, but we just don't know the answer. So there's no reason why it could not have had a magnetic field early on. There is no present-day evidence of global plate tectonics. So even though the planet has been resurfaced, it's not plate tectonics that's doing the resurfacing. At least not the kind of plate tectonics that we think about. So they believe that there's these seeps, basically these magma upwellings in different places across the planet, and that's where it comes from. And you see that in these coronae, they're called, these very large volcanic features on Venus, and those have played some part also in the resurfacing. There is some present-day evidence of volcanism, not only from the sulfuric acid that we measure in the top of the atmosphere, but Venus Express, this European mission that just finished last year, did detect some active volcanism in this Mokidaniki crater. So we see active volcanism today on Venus. To get a better handle on that, there is a proposal that has been put in, a discovery class proposal called Veritas that's run out of JPL, I believe. And their idea is to map the surface of the planet at very, very high resolution, horizontally and vertically, to get a better idea of what's going on the surface of Venus, whether there is plate movement or exactly what's going on with the surface. We'll know in the fall whether or not it gets selected or not. And as I said before, we really need these in situ measurements of these heavy noble gases and their isotopes and several other things to put better constraints on the history of this planet's geology. And there is another stage 1 discovery proposal that was awarded to a team at Goddard Space Flight Center led by Laurie Glaze called Da Vinci that is supposed to do exactly that. It's a mission that basically comes into the atmosphere, floats down, it measures as much as it can on the way down, and then it dies at the bottom. It's crushed to death by the 92 bars of CO2. So we'll know in the fall whether that mission gets selected. I think there were 5 that were chosen. Originally, the idea was to pick 2 Discovery class missions, so people in the Venus community were very happy that there's a good chance that one of the 2 Venus missions would be chosen, since, as I said, Venus is kind of a neglected stepchild of the terrestrial worlds. But I recently heard that because of problems with, I think it's the Mars 2020 mission, there's a delay in that, and that's going to eat up enough budget to prevent 2 missions. But I hope that's just hearsay and that's not true, but we'll find out. We'll find out this fall.
Mike?
Yeah.
There has been a lander on Venus.
There have been several Soviet-era landers. They did last for a few minutes on the surface. They did take some measurements, but the error bars on the isotopic abundances of these noble gases are really huge. There was another, quote, I mean not balloon-borne, but another instrument that we sent that also went through the atmosphere and measured abundances of several gases, but again, the error bars are quite large on those. So the idea is to send better instrumentation this time to get better constraints, in essence.
And Veritas would be a lander, or?
No, Veritas is a satellite.
Okay.
It's basically the same as Magellan. Magellan was the radar mapping satellite that was launched in the 80s to Venus, but this would be a much higher resolution satellite. I think there's a little bit on Wikipedia on each of them, but not much. When I wrote Lori to ask for details about Da Vinci, she wouldn't tell me anything by email. She said I had to come talk to her because there's some embargo stuff. I don't know. Probably Brian knows more about that stuff. But there's little bits on the web, but not a lot about these missions in detail. I don't know if there'll be European partners in these missions or not, because it's very hard to get information about them. Okay. For those of you that work here, I will just point out which version of the model I'm using. I'm working on something called the planet branch, which I don't think almost any of you have ever heard of or used, but it's a derivative of the master branch, but they're very close to each other. That's where we do experimental stuff like play with the calendar, play with the atmospheric mass, stuff like that of our world. It's an old 4x5 version, that's so that we can run a lot of simulations. I'm going to show you another parameter study at the very end of the talk. 20 layer in the atmosphere and a fully coupled ocean. So this is a fully coupled run. I use modern day Venus topography, mass, spin, everything. I think it's better than what most people use, which is Earth topography. It's probably the least worst choice you can make, since we don't know anything about the early topography of Venus. So that's why I chose it. I think it's the least worst. And of course, my atmosphere looks a little bit like Earth for reasons that we can discuss with our radiation people. I just pick a bar of N2, and I'm not the first to do that. I'm picking these numbers because other people have chosen very similar numbers for early Venus studies. And then, of course, the normal amounts of CO2 and a little drop of CH4. I use a solar spectrum from almost 3 giga-years ago, printed by this guy, Mark Clare. That's about 82% of the present day solar luminosity, so this is modern, and this is what the spectrum I actually use. So we were able to put different kind of solar spectra into Model E these days. That's thanks to a lot of work that Nancy did with a graduate student to get that stuff working.
Mike?
Yeah.
Today, I mean, a lot of the radiation is affected by the aerosols, by the haze layers and so on. So that's also in here?
This is an ancient Venus, so I'm not talking about hazes or aerosols. All that's taken out. There's no aerosols in this particular run. Our idea is actually to put some hazes into this model down the road, and Sean Goldman's group at Goddard is going to work on that for us.
So the idea is
and
really
Costas also.
The haze really came about when it started heating up. That's so at first there was no haze, and when Venus was heating up,
when is when?
Yeah, I don't know. I'm just wondering. So when does this haze come about? So you can completely ignore it now.
Yeah, we're just going to ignore it for now.
Yeah, okay.
The idea is just to put a simple thing together, and we will add more components as time permits.
I guess you're talking about the sulfuric acid haze, right?
Yeah.
Yeah, that's modern.
That's modern.
modern.
Oh, that's the haze you're talking about. Oh, I thought you were talking about an ancient haze. No, yeah, the sulfuric acid haze is a modern haze. We don't have a sulfuric acid haze on this world.
Yeah.
Why do you think that is?
Yeah, okay.
That's why you went around.
That's my around.
Acid rain.
Okay. So that's what the topography looks like in my rough 4x5 on the upper left. Because, as some of you know, our ocean doesn't like to freeze to the bottom, I have cleaned up the topography a little bit, which is what you see over here. Basically, when the ocean freezes to the bottom, the model doesn't like to change land type, and it crashes, and I want to avoid that if at all possible, so that's why I've cleaned up the topography a little bit, taking away some of the small islands and small crevices down here, which would normally build up ice and the model would crash. Yeah.
So, are this topography, is it kind of continents and ocean, anything like continental and oceanic crust?
I'm getting there, yeah. Oh, does it look like continent or oceanic crust? We don't know. We don't have the observations to say whether the rock looks like what we consider.
So we just know that it's higher in some places.
Exactly. So what I have done is I've taken this Magellan data from the 80s, I've ingested into the model, and then I pick what they call the mean radius of the planet. That's what I did. I picked the mean radius of the planet as my place to decide whether to put water below that or land above it. And that actually worked out to give me a 310 meter depth ocean, basically.
Well, actually, is there anything, do we observe anything like continental shelves or anything, or is it all just very gradual?
Because the planet's been resurfaced in the last billion years, we do not see anything like continental shelves. And you can see that here in these plots. So on the top here, you see Earth land volumes. These are histograms for height.
I see, and they're at the bottom, we see the continental shelf.
Yes.
That is continental.
Exactly. So on Earth, you have a bimodal distribution. On Venus, you have a unimodal distribution of material. And the same for Mars. It has a unimodal topography, basically. So that's what the Venus topography looks like. You can see how much land volume there is. They're not completely off for land, but of course the ocean volume is off by an order of magnitude, as you would expect when you have super deep oceans on Earth, which we do not have here. And again, that just depends on what depth, I choose, where I put that line to pick the water or not. So I had to pick something, so that's the number I picked. Okay, so let's show you some results, since you know what I put into the model. So this is a snapshot. It's about a sixth of a diurnal cycle. Since you guys know what diurnal cycle is, I won't talk about Venus days, but Venus solar days, 116 Earth days long. This is a sixth of a diurnal cycle.
Sorry.
And what you see here is that the surface temperatures for this model are not crazy. So it's going from about minus 30 on some of these continent-like structures over here to about plus 30. The mean surface temperature is about 284. And I'm going to show you results from a 1D model in a moment where they get a value of about 300.
Why do you think that continent thing attracts so much coldness?
Because it spends a lot of time looking away from the sun.
Okay.
The days are 116 Earth days long. So they spend a lot of time.
So you can't get the ocean circulation to keep it warm.
Well, I would say minus 31 in these places is probably a lot warmer than it would be otherwise without ocean circulation. Yes, it could be much colder if you spent that much time away from it. And I have some simulations with even more slowly rotating worlds where the temperatures are cooler, actually.
Plus the planet rotates the other way around, right?
Also.
So wherever you have a hot ocean, you will expect to have a warm continent on the other side.
So, just to make you realize it's not that different from Earth, here's a histogram of the land surface temperatures and the sea surface temperatures here. And they're not completely different from each other. Doesn't look totally crazy, as you can see there.
But habitability would have to do with the standard deviation to that diurnal cycle also.
Absolutely. Which I haven't looked at. I need to look at some latitude Here's a comparison to a 1D model from 2003 by Grinspoon and Bullock. These are two of the Venus experts in the US. You can see they use a very similar atmosphere to what I have used. 1 bar N2, 0.35 millibars of CO2. They pick 100% cloud cover. You can imagine why they pick 100% cloud cover, because it gives them the surface temperature they're interested in. But I'm going to show you why that works, in essence. And they get a mean global surface temperature about 300K. They
Isn't
run.
that the
Sorry.
1D models can handle either 0 or 100% cloud cover, but not anything in between?
I thought that there are some that can handle
Some.
some. Yeah.
Some.
I don't know
This
about
is
this.
a 2003 paper, so that might be not be one of the some.
Okay, so maybe that's why they chose it. But I mean, it was a good choice in the end.
Okay.
In theory, I'll show you. This is what the temperature profile looks like. But they picked 3 different kinds of atmospheres. I'm just talking about the 6 millibar atmosphere they chose. They used a 60 millibar H2O atmosphere and a 2 bar, where the temperatures of course go very crazy. But this is their 6 millibar atmosphere for H2O, and you can see that our temperature profile is not that different. This is what the water profile looks like. So we start with around 6 millibars at the surface with this. Okay, so what's going on here? So this is a picture of the high level cloudiness from the model that tells you why the planet is not baking, basically. And that's because there's a huge cloud front here that has increased the albedo of the planet on the side that's facing the sun. So this is the substellar point right here, and you get a huge cloud bank showing up there. Why that is? I have a slowly rotating world. So I don't have a lot of Coriolis force to break up my Hadley cell, so my Hadley cells are huge now. We see that in present day Venus. There have been measurements of the Hadley cell in Venus present day up to 70 degrees at least. So that is what causes this effect, is this very large Hadley cell, in essence. So that's why I want a slowly rotating world, to get that very large Hadley cell, in essence. So for the clouds people, I thought I would talk about what kind of clouds they are. They are the bottom water clouds, as you can see here in this latitude pressure plot. And at the top, they're ice clouds. Tony tells me that this is an artifact of the 4x5 model's low top. I just talked to Max a couple days ago about trying to use a 96 layer model to see what it looks like if we do that. He said it's possible. And then cloud ice water content and cloud liquid water content. So that's what the clouds look like.
What's the scale?
This is just, oh sorry, this is from, yeah, sorry, I got these, these are courtesy of Tony Del Genio, and he did not give me proper scale, proper fonts. So this is 0 millibars, and this is 1,000 millibars.
0?
Surface. Sorry?
0 millibars.
Well, I mean, whatever. This is the top of the model.
Yeah, okay.
This is the bottom of the model. Okay. Is that enough? Here's the top of the model, here's the bottom of the model. Here's about 300 millibars. 300 millibars.
Okay.
So the
And
transition
Tony,
occurs right around 300 to 400 millibars, basically.
but so that upper layer, Tony says that it shouldn't be there. It should be lower, or
He just said it's an artifact. I don't know what he meant by that. That's just what he told me. So I figured one of the clouds people would speak up, as they are now, to ask me what on earth that is. So I had to put something there, because I knew I would get a question about it. But not being a cloud expert, and I'm not an expert in this part of the model, I don't know what it is, but that's what he says it is. So he thinks if we run it with more layers and higher atmosphere, that should go away.
The 96 layer at the same height. We do 102.
Well, same height with 40. This is a 20 layer.
This is a 20 layer model.
What's it? 20 layers.
So you can go with the 40 layers and get the same height with the 96.
Right.
Without getting the...
Oh, sorry, I didn't mean 96. I meant the 108. That's what I meant, I think. I wanted to
Okay,
try
so
with
you
the
really
super-
want to go very high.
Well, I would like to go higher for other reasons too. I would like to see if the model can put some constraints on what the atmospheric escape would be for various model runs I'm doing. I don't know if it can, but I would like to see.
I don't think it can do that.
Okay, well we should investigate that.
What's the yellowy white water content and ice water content number?
That's 0.06.
mastery.
Oh yeah, sorry, 0.6 times 10 to the minus 30. Okay, I'll have to do proper plots with proper limits. I didn't think this would
Yeah,
be so
that's
bad.
10 to the minus 3 kilograms per kilogram, right?
Yes.
Okay.
Okay, that's what the albedo map looks like. Not surprising from what you saw of the cloud bank. I think you know why there's no albedo over here. So it's got very high albedo, as you would expect from what we saw in the clouds. That's just for people that don't know what a Hadley cell is. I think everybody in this room knows what the Hadley cell is, but that's what the Hadley cell in this world will look like. A single Hadley cell that causes that very large convective cell to show up. Okay, how about my more speculative stuff? If Venus was one of the early habitable worlds, could it have seeded Earth instead of the other way around? And maybe 20 years ago, there was this idea that since Mars cooled first, it was the first world that had a chance to get life going, and it might have seeded Earth. But then we discovered that that's not a good hypothesis given the Feng Young Sun problem. But Venus is probably the more likely world if certain circumstances are met, as you can see, to be a better place for life to start. And there is several papers that look at mass exchange between the terrestrial planets, and it's definitely possible. It's not as easy, of course, to get material from Venus to Earth as it is to get material from Mars to Earth. But I gave this talk over in the Earth and Planetary Science and Astronomy departments at the Museum of Natural History, and I invited the meteoritics people to come to the talk also. And I asked them point blank about this. I said, well, we have Martian meteorites. Where are Venus meteorites? They said they don't know if they have any, because we don't have enough information to know if we have Venus meteorites. We didn't know we had Martian meteorites until we sent landers there and figured out the isotopic abundances of these rocks and realized we had Martian meteorites sitting in our museums. So if we can get better constraints on these isotopic abundances for Venus, we'll probably find some of these rocks in our museums, and we can use them to do all kinds of studies as we do now with Martian meteorites. As you're
But you
probably
need
aware.
the surface information before the resurfacing.
I'm not sure you need I'm not sure that's true. I think if you can look at the noble gas abundances, those probably have not changed. That's why people like to use them, and that will tell you what you need to know. That's the idea.
Do we have a theory of how these mass actually got here?
Large rocks hitting large planets, knocking pieces off, and then they come out. They can reach the escape velocity of the world.
They think that, how long do they think? Is it a million years to get here, or a billion?
It depends on the orbital configurations and what the mass of the rocks are and all kinds of things, but they're in the papers. It's millions of years for most of the scenarios, absolutely. Okay, so I just wanted to touch on why this study was begun is mostly because we've been doing a series of parameter studies looking at how Model E reacts to slowing down an Earth-like world and increasing the solar insolation, because we're finding all these exoplanetary worlds around stars in our neighborhood, as you know. And we see, for some of them we have some rotation rates, but not for many. But the idea is to figure out how these planets' climates would respond if they're rotating slowly, and if they're closer into their stars. So this is a parameter study where we're probing the inner edge of the habitable zone, as we call it. So you can see here, this is a normal Earth world. This is an Earth-like world that has a day length that's 16 sidereal days long instead of 1 sidereal day long. These are sidereal days. This is 64 sidereal, 128, and 256. And I had noticed in a previous paper that people had put Venus down in this regime, so I wanted to test it myself, and I found out, yeah, it sits down here, and the globally average surface temperature is not too crazy in that world, and you saw those results. So that's where this study came out of. But there is one thing that has not been discussed that much in the literature about this stuff, which is will such worlds lose their water anytime soon? So there's a variable, there's a number you can calculate called the casting water loss limit. It's basically how wet is your stratosphere, because if you get a lot of water vapor high up in the stratosphere, you can get dissociation and you start losing your atmosphere. This line is the casting limit. Here's on a linear plot, this is a log plot. And you can see that you don't have to get very warm for Earth to reach that casting limit. This has been discussed many times. This is this kind of moist greenhouse limit that people are so concerned about. Often when you see pictures of habitable zones for the solar system or for other worlds, Earth is right up against the inner edge, as they think, and that's part of the reasons why they keep Earth so close. It doesn't take long for the moist greenhouse to go into effect. But for these slowly rotating worlds, you have to get quite hot before you really start dumping water vapor up in the stratosphere. And the same for Venus. When I do it for Venus, it's for that Venus run I show. It's very low. So that's a good sign. There's not a lot of water vapor up there. Okay.
That's stellar flux, right?
Yeah, that's still a flux.
So are the albedos the same?
Are the albedos the same? Well, it's whatever the model puts out. I don't set the albedo in the model. So all these
that
runs.
that might affect a lot how much of the stellar flux actually makes it and stays in the panel.
Of course. Yeah. But I let the model decide the albedo. I'm not running a 1D model. I don't decide the albedo. All these runs start out with a kind of simplified topography, again, because of the ocean problems. We start out with no land ice. We use a fixed land albedo. There's no vegetation, and then we let the model evolve.
Do you see any sea ice developing?
Absolutely, depends on the run. All these have zero obliquity, so you often get sea ice at high obliquities, which is one of the first problems I ran into with the ocean, because when you have zero obliquity, you run Earth with zero obliquity in our model, it will crash within a few hundred years, because the sea ice builds up and the ocean freezes at the bottom and then you're finished.
With the aquaplanet, I had the same problem.
Yeah.
There was no content, so.
Yeah, even with an aquaplanet, yeah. Although, did you use fully coupled ocean? I think that
Yes, yes.
was it fully coupled?
So I had it with 1,000 meters.
Oh, 1,000 meters, okay.
But, yeah, obliquity, zero obliquity, 50 years in front.
Yeah. So those are some issues we definitely have. Okay, so almost conclusion. So that's my hypothesis, that Venus, not Earth or Mars, was probably the first habitable world. I told you what kind of assumptions I've made, and I think you have to make less assumptions for early Venus than you do, at least for Mars, maybe not for Earth, of course. We really need these in situ observations to get a better handle on that water inventory. That's the key thing, because there's a lot of theory that says that Venus lost a lot of its water very early in its history because it was closer to the sun. Its magma ocean stayed around a lot longer, and a lot of the water in the mantle of that world was outgassed, and then it was basically stripped off. It was disappeared. So we don't know the answer to that until we get better isotopic abundances. So that's my last Martian reference. As I said, I started out with pro-Mars, again, kind of pro-Mars and pro this guy. But I thought I would show you something kind of fun. So since I was doing this work, and I teach some high school students down at the Museum of Natural History a couple times a year, I asked these students who don't know, you know, they took an astronomy class, right? They're like the best high school students in New York City, what Venus looks like. So here are some examples from my students. These are juniors and seniors in high school, basically, some of the finest high schools in our city. And this is what they think Venus looks like. I think only
I'm guessing you're going to STEM schools and not art schools.
I gave them a large selection of crayons to choose from. Here's some more strange colors here.
I think I would have done about the same. Well, not
Here's a nice ring system. I think this looks like a world that you're familiar with, a gas giant somewhere in our solar system. I'm not sure what this is, maybe a black hole.
Oh, that's nice. Top left.
Yeah, top left. Yeah, she pulled this one on me. I told her not to do that. Here's one with kind of a dot on it. I guess that's a great the great spot on Jupiter. Here's some really nice ones. Saturn. This child had it correct. She's a Hunter student, so you would expect that she would be that way. She told me these are sulfuric acid clouds and that it's yellow. She was the only one that was totally on it. You can't see it in this display for some reason, but this is supposed to be the Venus de Milo that was drawn by one of the students. Sorry you can't see that. It's a very nice drawing, but it doesn't show up on the screen.
You can imagine.
And then for Thanksgiving, I tortured my family and made them give drawings of things, and you can see these are some of the younger children, my brother's younger children, and family members. I don't know what this is.
Pizza.
Pizza. Yeah, we're doing pizza.
It looks like 10 years gave your high school students very little benefit.
Yeah. Well, these are not my family members. They're even worse. This is my brother's oldest son. He's saying this is Venus,
Yeah,
not
Venus,
Evan, obviously. But this doesn't look too bad.
What's that at the bottom right?
I don't know. Probably
Uranus?
Neptune.
Uranus, yeah.
Uranus. Yeah, I think they're getting them confused. It's a little disappointing, I know. That's the state of our educational system. Anyway, that's all I had to say. Thanks for coming, and ask me more questions, or tell me like how far out some of the assumptions I made. I think I know all the wild assumptions I've made, but the idea is to write something up on this and then put all the caveats in and try to put constraints on. I mean, one of the biggest problems is trying to figure out what the early atmosphere of Venus could have been like. That depends on, nitrogen outgassing rates. Was there a carbon cycle? Things like that, weather angles. Yeah.
So your plots seem to, and that's very, I don't want to say convincing,
Because you're not convinced.
Well,
Thanks, Bob.
very, very convincing for the idea that, if we were planning a mission to go colonize the planet, and you showed those sets of graphs, saying, wow, Venus is a really much better planet. It's more stable in all these measures.
It was. Was.
Yeah, so it's more stable to changes, for example, changes in solar radiation. So then the question is, well, what happened? So it was so stable, did the
Okay.
sun just go outside its zone or what?
One thing I didn't show you, well, I did show you, but I didn't stress it, is this. So here, I increase the solar insolation for these other worlds. They're very much like Venus, at least in terms of rotation. Atmospheric constituents aren't necessarily different. So you can see the global surface temperature is not going up that much for quite a lot more solar flux.
That's right.
But you have this problem. You have the water loss limit problem. And by the time you get up to these kind of numbers, you start having problems. Because the stratosphere starts getting a lot of water vapor in it, and you start having to worry about
Yeah, but the Earth
loss.
would have gotten that problem so much earlier.
Oh, Earth, yeah, because it's a fast spinner. Yeah, absolutely.
Yeah, so
That's what drives it.
so you failed to
But
Sorry?
Earth is not there yet.
I see. So what are the solar fluxes today?
1360 something.
13, see, they're way down here.
And for Venus, what is it?
Venus, well, the Venus is right around here, so around 1900
Okay.
is where Venus is. So right
look,
around.
look, Venus is 1900 on the Venus plot is nowhere near its Casey's limit either.
No, but as I said, I mean, the idea is to study this for early Venus, 3 billion years ago, and the idea is to step it up. I'll step the model up, increase the solar flux, and see when it actually reaches that.
But where is Venus today?
Where is?
What's the solar flux on
Oh,
Venus
it's
today?
I think it's is it 2700? I think
Okay.
it's quite far. It's quite far.
So really, the problem really is that it just got pushed past its limit.
Yeah, but what was the limit? I mean, how long was it there? Was it there for 1 billion years? Was it there for 2 billion years? Was it there for 3 billion years? We don't know. So one of the things we want to know about these worlds we're going to find is how long were they in the habitable zone? It's not only that it's in the habitable zone today, how long has it been there? Has it been there for 500 million years? Has it been there for 1 billion years? For 2 billion years? How long is it going to remain there?
One
So there's
thing
all questions we want to ask.
One thing I take away from this is the habitable zone depends on the rotation speed of the planet.
It is one of the things that is very important. Yes.
Right. The whole lingo we're talking about a habitable zone as if it's a specific, absolute zone.
Yeah. There's a lot of complaints about that definition, and there's a lot of pushback against that now, and that we should have, a PDF really. But there's so many things that can go into it. For example, I showed you that Venus has almost 3 bars of N2, right? As you know, there's some very good nitrogen sinks here on Earth, and that's a lot of that's driven by biology. So what if you don't have nitrogen sink on Venus, and the nitrogen just builds up and builds up and builds up? What does that do? That line broadens all of your greenhouse gases like CO2 even more, so they become more potent, so the planet heats up even more. So that's one constraint that we would need to set on these worlds. Like, what are the atmospheric abundances for these things? What is the, how much pressure does the atmosphere have? Which is very hard to know. So that's why I put in one of those early slides, the sinks for nitrogen, the non-biological sinks for nitrogen, we don't think take a lot out of the atmosphere. They're not very efficient. So that's probably why it has 3 bars of nitrogen today.
So when does carbon dioxide start to play a role in all this? So you're showing the water vapor loss as things the sun gets brighter.
Right.
At what point and by what mechanisms do you start getting large amounts of CO2 coming into the atmosphere?
I would guess it's when the weathering process starts to become less efficient, right? Because as the planet gets warmer, the carbonate rocks don't interact with the silicate rocks don't interact with the CO2 very well, and of course as the oceans get warmer, they don't dissolve CO2 as well. So that's kind of the feedback that I think we discussed in this building about climate change, right? That as things warm up, the process becomes less efficient. Absolutely, but that's not a fact. We don't have anything like that in the model, of course, because you have to do runs over, obviously, millions and millions of years, which we don't do. So we don't have a weathering in our model or anything like that. So, but it's certainly something that can be calculated. It has been calculated. What's the efficiency of the CO2 weathering process?
So, any idea on what time scales are for as the sun's brightening and you're losing your water versus the CO2?
Yeah, I have not done those calculations yet, but those are things that I want to look at, absolutely. I've been talking, after I went to this conference in Japan, I've been talking to Norm Sleep. He's he's a well-known planetary geologist, and I wanted to talk to him about some of that stuff, so we've been corresponding now. And he sent me a stack of papers, which I'm trying to get through. Half of them authored by him for the past 30 years. So yeah, that's another factor that has to go in here, absolutely. So this is just the first step, kind of to see. I was just surprised how well the world did, making not too many crazy assumptions, I thought, and how it turned out. And I think, as I said, the assumptions I've made are not as crazy as some of the assumptions they make for Mars, where with Mars you'd have to have a really, really thick atmosphere. And then it has a really hard time hanging on to it. You can get a lot of volcanic outgassing on Mars for a few million years, but then it just can't hold on to the atmosphere. It doesn't have a magnetic field. It just it gets stripped. So yes, Mars probably had water, but the question on Mars really is how long did it have the water? And I know people love the idea of looking for subsurface water and hoping that through underground heating and stuff like that it could work. But I think you would want to say the same things about Earth, because early Earth was also quite cold, and we don't know where the first life forms began. It seems like there's a consensus now that the first life forms were definitely not these organisms we find in hydrothermal vents, which was believed very strongly 10, 20 years ago. But that's now, through phylogenetic studies, I think that's been thrown out. So they don't know what the first life forms really, where they came from. We don't know what do they call it, the first common living ancestor. We don't know what that is. We know that these black smokers and stuff came after that. So we don't know. Until we know that for Earth, it's going to be very hard to say what it is
Right.
in other worlds, basically.
I would like you to add some Gustav Holst to your multimedia presentation.
Okay, I will add some, to my planetary.
A little bit of Venus.
A little bit of Venus. Okay, I'll do that.
A little bit of Mars, the inner of war.
It's hard on these computers because the speakers keep getting smaller and smaller. It's not a good effect, but maybe there's a better. Well, there are some speakers. Okay, so next time, Brian, I give this talk, I'll plug this one. Thanks for the advice. Okay, any other questions? All right, come talk to me afterward if you have other ideas.